A machine learning methodology for diagnosing chronic kidney disease. A review. As a quick review, chronic kidney disease is a world health problem that affects nearly 10% of the world's population. Unfortunately, one of the reasons it is so prevalent is due to its subtle nature. In its early stages, there are no noticeable symptoms, and in most cases, a patient will lose up to 25% of its function before symptoms even occur. Hence, having a way to detect it early is essential for the survivability and the quality of life for any high risk patient. Technology has been able to facilitate the collection of medical data, which enables scientists and researchers to dive in and attempt to predict and classify potential cases. Machine learning can then be used to diagnose patients because of improvements in the electronic health record. The data that was used in the study was retrieved from the UCI Machine Learning Repository. The data set is composed of 400 samples that contain 24 predictive features, 11 numerical and 13 categorical variables, and a target class denoted as having and not having chronic kidney disease. In order to standardize the data, all categorical variables were numerically encoded. The data is slightly imbalanced, where approximately 60% of the samples had CKD and 40% did not have CKD. In addition, there were numerous missing values in the dataset. In order to infer the values, KNN imputation was used to fill them within the range of similar samples. Since KNN imputation is dependent on the number of K values, 5 different imputations were produced at varying K levels. Additionally, to establish the performance of the imputation, it was also compared against using mean, median, and random values to fill in the missing values. After the data has been standardized and pre-processed, the study compared 5 different machine learning algorithms to model the data: logistic regression, support vector machines, k-nearest neighbor, naive Bayes, and a feed-forward neural network. In order to compare the performance between the 5 models, accuracy, recall, specificity, and F1 score were used. The performance was compared across all 5 different imputation iterations, and the results are listed in the table to the right. Overall, there were mixed results, but leaning more towards random forest and logistic regression as the better performing models. Random forest achieved the best performance with 99.75% diagnosis accuracy. However, because of the mixed results, there is still some room for improvement, and perhaps an integrated model would be better suited. The models that were evaluated all had different strengths, and in order to achieve better performance, an integrated model is considered. In order to choose the best components for an integrated model, misjudgment analysis was performed. Essentially, one compares the misjudged samples from different models and chooses models whose misjudged samples between the other models are different. In the study, it seemed that all the samples that were misjudged by the random forest could be correctly judged by the rest of the models, which means random forest could be used as one of the components. Overall, logistic regression seemed to be the best model to pair with the random forest due to its accuracy and performance. In order to integrate them into a perceptron, the probabilities of each model were then used as outputs for their underlying components. Next, in order to evaluate the performance of the integrated models, it was evaluated 2 ways. First, simulations were run on each imputation iteration dataset with a preset random seed, followed by simulations without the preset random seed. In nearly all cases, the integrated model outperformed the individual base models, achieving on average a 99.83% accuracy. The researchers have shown that this methodology they chose, which includes using KNN imputation and an integrated model, is an effective and feasible means to potentially classify a CKD diagnosis. Finally, the study overall shows a lot of promise for it to be used for an actual medical tool. The researchers showed a clear, well thought out process to find the best performing classifier for identifying chronic kidney disease. The researchers were systematic in their approach and were able to handle the missing values in the data by way of KNN imputation. The most fascinating approach I learned was to use an integrated model in order to leverage a model's strong points. This is something that could be used in the final project in order to achieve a stronger performance. The study, however, was not without some points of improvement. For instance, the researchers do not handle the imbalanced nature of the data, where the split is around 60-40, having and not having CKD. This may impact the balance of the results by over-predicting having CKD than not having CKD. In addition, the study was conducted on a very small sample size, which may impact the generalizability of the model itself. In the future, perhaps a much bigger data set will help achieve better performance. Finally, the model only classifies the existence of CKD, but it does not help determine the severity of the disease. In the future, perhaps a different model could be used to determine severity.